Greetings, math fans. All right, this is day 7 of chapter 1. It's the last day of the chapter. Um, Before I actually get started, I just want to remind you guys this is actually a very challenging chapter just for the quiz and the test because there's a lot of material, and I gave you guys a lot of notes on all kinds of things with logs, parametrics, even odd functions, putting things in different forms, whatever. Make sure you study this. All right, this is not. It really is not an easy chapter, and I just want to make sure that you guys hear this. If you're listening to this video, maybe you're missing the last day, that it's a challenging quiz and test, and you need to study hard for it. All right, so let's get started here. Again, this is day 7, and I really want to talk about a little bit more about logs. All right, we've actually talked about solving logs, log problems, and everything using the graphing calculator, using some of your log properties. And we're going to do a little bit more of that today. The first thing I want to talk about is graphing logs. Okay? And what I want to do is I want to graph y equals log base 5 of 3 minus x. Now that's pretty challenging, and the reason it's pretty challenging, math fans, is because you have log base 5. Your calculator basically has log and ln, and if you already know, the log means log base 10 and ln means log base e. Okay, you don't have a log base 5. So what you really need to do is I need to convert this to an exponential function, and if you remember, if I look at it, it's 5 to the y power equals 3 minus x. So 5 to the y power equals 3 minus x. Now you guys should know that from algebra 2, rewriting that, right? The base equals, or base of the answer equals whatever taking the log of 3 minus x. So I'm going to solve for x, and I'm going to get x is equal to 3 minus 5 to the y power. All right, well, still, my goal here, math fans, is to graph this. And as you already know, you cannot graph an x equals problem on your graphing calculator. But what can I use instead? Okay, now remember what we've been using a lot is parametrics. That's exactly what I can do. So we're going to use parametrics. And so what we're going to do is we're going to say our x sub t is equal to 3 minus 5 to the t power, and y sub t then is just going to be equal to t. Right? That's a nice use of the parametrics. Okay, so now let's graph this on our TI. I'm going to pull up my virtual TI, and I'm going to type it in here. Make sure you're in parametric mode, of course. And we're going to get x sub t is equal to 3 minus 5 to the t power, and y sub t is just equal to t. Okay, and it's probably good to use Zoom 6, Zoom standard. Now, it's okay to use that, but this is the graph that we're given, and it's like, well, what does that really show us? It's really small. I can zoom in, so let's try a couple different things here. So if I do zoom in, zoom 2, and hit enter. Okay, well, I see it's definitely going way out to the left here, but what's going on right over here? Okay, and so what I want to do is, if I hit the window, which you might break it if it's made out of glass. No, I'm just kidding. Notice when you hit zoom standard, t min is 0. Okay, because usually t starts at 0. All right, so what you need to do is I need to see what's going on past that. So I'm going to go actually try negative 10 to 10. And I can see right off the bat, see this graph down here below, math fans? Okay, this is actually what I'm looking at. Let's actually graph it on top here. And there's my graph. So this is actually going down. I'm going to zoom out a little bit. Ah, look at that. It's going down like that. So there must be an asymptote over there. Okay, so that's just kind of interesting. That's kind of what our graph looks like. So let's go back to our information here. So the graph, if I kind of graphed it, it's going to look kind of like this, right? That's what the TI gave me. Okay, but again, you got to adjust your window to make things look good. Let's talk about the domain and the range, because that's kind of important for this guy here. So the domain, well, remember this value, if I look at this guy here, this value has to be greater than 0. You can't take the log of something that's 0 or less, right? So basically what I'm saying is 3 minus x has to be greater than 0. So negative x is greater than negative 3, divide by negative 1, x, don't forget to switch around the inequality, x is less than 3. So there we go. There's my domain. It's between negative infinity and 3, not including 3. Okay, that's pretty easy. Now let's look at our range. Actually, just based on the graph, it looks like it's hitting an asymptote here, but truly it's not. Okay, because don't you guys agree that y value can keep getting bigger and bigger and bigger? All right, like if I take, here, I want to bring up my calculator again. And right, let's say I know I'm not going to do log base 5, but I'm going to do log base 10 just to kind of show you a little bit. If I do, so let's quit out of here, log of just some big number. Let's just choose whatever number that is, 100 million or something. Okay, it's 8. Okay, so it doesn't go up very fast. That's why it looks like it's an asymptote, but actually it's going to get bigger. I can type in log of a trillion, and it's going to be even bigger and bigger and bigger. It's going to go up very slowly, so that's why it's almost a horizontal line, but it still is getting bigger. So in other words, it can go up higher and higher and higher, so it's positive infinity, and it can go lower and lower and lower. And of course, look at that. You can look at the graph down here, right? Isn't that graph going down to negative infinity? Okay, so basically if I do, the reason it's doing that is because if I type in log of 0.000001, so I'm getting close to an asymptote, I get negative 8. So it's the x value is getting closer to some value, and the y value is it's continually going down. If I put more decimals in there, it'd be negative 9, negative 10. So going back to here, my range for this problem is between negative infinity and positive infinity. Okay, logs can be positive and negative. It's just what your input is into it has to be greater than 0. Okay, so again, just be careful again on your graphing calculator. Make sure you set your t values, not between 0 and 2 pi, which is what my calculator was when I hit zoom standard, but maybe negative 10 to positive 10. See what's going on around different things. All right, and check some things out. Use your zoom feature. A lot of different things, but set your window sometimes manually really helps out. All right, so the next type of problem we're going to do, math fans, is we're going to talk about just some of the properties of logs. And that's actually on page 41, 42 of your calculus book. And I'm making this video in 2011, so hopefully it doesn't change too much. But your textbook does list the properties of logs. It might be a good idea to review that. We're going to talk about that now, but just to have for future reference, that's not a bad idea. But these are some inverse properties of logs. Again, it's page 41 and 42. Okay, the first one we're going to do is a raised to the log base a of x that equals x. Okay? And again, I hate to just hand you this stuff because you look at it and you go, yeah, okay, I guess I believe you. You're the math teacher. I would rather you kind of understand that this is true. And there's one way I can prove it is by actually using my properties of logs. Okay, if I take the log of both sides, so watch log base a. We'll take log base. You can take log of anything. You can take natural log. You can take log base 10, whatever. But if I take log base a of a log a of x equals log base a of x, right? Doesn't this go in front? Doesn't the exponent go in front? So I really have log base a of x times log base a of a equals log base a of x. Okay, and I can divide both sides by log base a of x and get rid of that. And what do I have? I have log base a of a equals 1. And if I write that as an exponential, isn't that a to the first power equals a? Yep, that's true. A equals a. Whoa, a equals a. All right. So that's the first property. So I numbered it here. It's the first one that's important. All right, let's look at the second one. Log base a of a to the x equals x. That one's actually a little bit easier. Okay, because this one I can just write as an exponential. I can do a couple different ways. I could bring this x down if I wanted. So I have x log base a of a equals x divided by x. They cancel. I have the same thing. Log base A of A equals 1. So A to the first power equals A. So A equals A. That's true. I could have also written this as an exponential, right? Log base A of A to the x equals x. I could say A to the x equals A to the x. A to the x equals A to the x. That's easy. So that's true. All right. So this is, let me write this out. This was our second one. It's log base A of A to the x equals x. Okay. And our third one is e to the natural log of x is equal to x. Okay. Well, this is pretty easy. What do we do? We're going to do to both sides when you have an e. Can I just take the natural log of both sides? So what happens to that? It goes in the front, right, by power property. So I get natural log of x, ln of e equals ln of x. I can divide both sides by ln of x, and I get ln of e equals 1, and ln of e is equal to 1, so 1 equals 1, and they're done. Okay, so that is my third property, inverse property is e to the ln of x equals x. All right, that's pretty quick, pretty mellow. Okay, so let's talk about some other properties of logs, some basic properties, which you guys actually learned back in Algebra 2. Properties of logs. Okay, well the first one is they're made out of wood. Just kidding. JK, JK. Okay, we're talking about the product rule. And that's really easy. It's log base A of x times y is equal to log base A of x plus log base A of y. Okay? That's pretty easy. So just remember, if it's multiplication, then it's addition of those separated. Okay? That's pretty cool. The next one we're going to do is quotient rule. So it's log base A of x over y. And this is just going to be subtraction. Log base A of x minus log base A of y. Okay, it's pretty easy. So it's top minus the bottom. Just remember that. It's very important. Okay, and then our third property here is the power rule. It's very powerful. You have log base A of x to the y power. That is, remember that you take that y and you bring it in front. So it's y log base A of x. Okay, it's pretty easy. And then the fourth one, this is a very exciting one. This is called change of base. Okay, I guess they call it base, change of base formula. That sounds good. Okay, so that's just saying log base A of x. So, like, it's really handy because if you don't have a log base A of x, if I say what's log base 2 of 10, okay, you don't know that, but what you can do is you can rewrite this as log of x over log of A. And these guys here are base 10. Or base E, doesn't matter. You have both of them on your calculator, but doesn't matter which one you use. Okay, you get the exact same answer. Very important formula here. Okay, so let's do some problems here. This is we're going to solve for y using properties of logs. Okay, so 3 to the y equals x. Okay, well, this is easy, right? This is all kind of old stuff. Take the log of both sides. Power property goes in front. So y log of 3 equals log of x. And then divide both sides by log of 3. So y equals log of x over log of 3. Okay, that's pretty mellow, right? Let's see. So what else can we do here? We can use the inverse property just because I want to show you how to do that, right? If I back to our original problem, 3 to the y is equal to x. So you could take log base 3 of both sides. So if I do that, log base 3 of 3 to the y equals log base 3 of x. Okay, and if you remember, just if you look back at our property, this guy right here, log base 3 of 3 to the y, is just y. Log base 3 of x. And you're like, well, wait a second, that's not the same as that. Well, sure it is. Let's change the base. So right, I can write it as log y equals log of x over log of 3. So these are equivalent. Okay, it's very exciting. Okay, let's try another example here. X equals 10 over 3 minus 4 to the negative y. Oh man, brutal, brutal. This is brutal. Okay, not really. So I guess solve for y again. So I'm going to put it over 1. We're going to cross multiply. And we get x times 3 minus 4 to the negative y equals 10. Okay. And then I'm going to divide by x. So 3 minus 4 to the negative y equals 10 over x. I'm going to subtract 3, so negative 4 to the negative y equals 10 over x minus 3, and I'm going to take the log of both sides. Well, I guess I'm going to move that. Let me get rid of this negative here first. I think that's a good idea. So 4 to the negative y equals, I'm dividing or multiplying everything by negative 1. So I really get 3 minus 10 over x, right? And then it's a good idea to take the log of both sides. So log here and log here of that whole thing. And this guy goes in the front then. So we get negative y equals log, negative y times log of 4 equals log of 3 minus 10 over x. Okay, and we just divide both sides by log of 4. It's messy, but that's what it is. Okay, and we get, I guess it's by negative log of 4. And so I'm just going to put the negative on top, but we wind up getting y is equal to negative log of 3 minus 10 over x divided by log of 4. You know, a little nasty, but that's what it is, man. It's solving for y. All right, that's not too bad. Let's try another one here. Okay, so our next example is with natural logs. So natural log of y plus 3 plus natural log of 5x equals natural log of 7 plus x. Okay, looks kind of brutal, all right, but yeah, it's not too bad. Okay, so the first thing I'm going to do is, again, I want to solve for y. So solve for y. Okay, so I'm going to isolate the y first. I'm going to have natural log of y plus 3 equals natural log of 7 plus x minus ln of 5x. Now what I'm going to do is I'm going to raise e raised to both sides. And some of you guys are going, are you allowed to do that? Well, sure. Think about it. If I have, let's say x equals 3, can I say e to the x equals e to the 3? Well, sure. Doesn't x equal 3? I mean, you know, I could have, 2 to the x equals 2 to the 7th. Well, x equals 7. So I'm allowed to, as long as I have the same base, I'm allowed to have the same base raised to that, whatever that each side is. And that's okay. So I have e raised to the ln of y plus 3 equals e to the ln of 7 plus x minus ln of 5x. All right, and remember your property, one of our inverse properties that we first learned here is e to the ln of x equals x, right? E to the ln of x equals x. So if I have e to the ln of y plus 3, that's equal to y plus 3. Sweet. Okay, and now this is a little tricky. It's e to the ln of 7 plus x. That's all the same power. Well, what do you have when you think about your exponent rules? Isn't 2 to the x plus 3? Isn't that the same thing as 2 to the x times 2 to the third? Right? Don't you guys agree with that? Right? When you multiply with the same base, don't you add the exponents? So actually I can simplify this. I can write this as e to the ln of 7 times e to the x times e to the negative ln of 5x. Alright, so I get y plus 3 equals, what's e to the ln of 7? Well, here, we're back to this again. E to the ln of whatever equals that whatever. So that's just equal to 7. Well, I can't do anything with e to the x because it's just e to the x. And what does that give us? It gives us e to the ln of 5x to the negative 1. Right here, I'm just using kind of properties of my logs there. Right, that negative goes as an exponent, doesn't it? So really, let's kind of keep going here. Y plus 3 equals 7e to the x. And then what do I do with this? Isn't that just 5x to the negative 1? Or 1 over 5x? So I get y plus 3 equals 7e to the x over 5x. Where do I have room? Right, let's do it over here. Y equals 7e to the x over 5x minus 3. Okay, so it looks kind of complicated, but as long as you follow all your properties, this is probably right here one of the trickier steps. Okay, because you have e to the ln of, it actually starts out here, right? Negative of ln. You can't do anything with that negative. You have to move it, because if I want to say e to the ln of 5x, I want to, that negative can't just go in front of the 5x. It's negative natural log of x. So I got to move that to the exponent. That's what I did here. And then that, when I do that, it becomes 5x to the negative 1, which is 1 over 5x. And then you simplify it. All right? So it's a little complicated, but not too awful, as long as you follow your properties of logs. Okay, and last example, it's actually a relatively mellow example. If I said natural log of y is equal to 2x plus 4, I don't know, it's like super easy. So I'll leave you on an easy note here. What do? You take, or you raise it to the e power, right? E ln of y equals e to the 2x plus 4. So that's equal to just y. And I have e to the 2x plus 4. All right. What's another way to write that? You can also write that as e to the 2x, e to the 4. But this is the best way to write it. Okay, so that is your answer. All right. Now, real quickly before I let you go from this video, number 49 in the homework, make sure when it says x equals 1997, you really let x equal 7. Okay, that's really important when you're doing your homework. Otherwise, your regression line is going to be super nasty. So just kind of follow what they say over there. Let x equal to 7. All right, that's it about all the log stuff here, math fans. I hope you guys kind of knew some of the stuff and maybe learned a few new things. All right, have a nice day, math fans. Adios. Goodbye.